So far we've been thinking of linear regression as fitting straight lines to the data. In this video we'll talk about the choice of features that we have, and we'll also talk about polynomial regression and see how that allows us to fit much richer, sometimes highly nonlinear models to the data as well. And underlying all this will be the same basic algorithm and mechanism of linear regression that we've been talking about all along. Sometimes in linear regression you have a choice in what features to use, or what are your input features. And in particular, using our long-running housing price example, right? Imagine that the features you have available to you are the dimensions of the lot, or the dimensions of the plot of land that the house sits on. So, let me draw a top-down view. So this is, right, if you're seeing the house, the satellite view of the house, and let's say that this rectangle is the plot of land, and so, your house is maybe somewhere on this plot of land, right? Sorry, terrible drawing skills, but that's your little house. And let's say this is the road that runs in front of your house. I hope this picture makes sense, right? This is a top-down satellite view, so you have, maybe some park cars there or something, okay? And those red blobs are my artistic rendition of a car view from top down. So it turns out the frontage of your lot is the width of the plot of land that the house lives on, and depth of the lot, D-E-P-T-H, is what we call how far deep. So from the road, I guess this black thing here, right? That's the road that runs in front of your house, and the depth is how far back from the road does your plot of land run. And so one thing you could do is model this as h of x equals theta 0 plus theta 1 times the frontage plus theta 2 times the depth, so you set feature x1 to be equal to the frontage, the width of the plot of land, and feature x2 to be equal to the depth, assuming rectangular plots of land. And you could try to use this to predict the price of a house. But maybe the price is a function of the land area, right? Rather than really a function of frontage or the depth, maybe it's a function of how much land area you have. And so another model you could instead build is to just have one feature, x or x1, which we're going to compute as the frontage times the depth, right? So it's the base times height of a rectangle is the area of the rectangle, so it's the size of the plot of land, and you can then model your price as h of x equals theta 0 plus theta 1 times x. And this latter one might be a better model. And to get there, what we did was we took the two features we had originally, and we used them to instead define a new feature, frontage times depth, which happily corresponds to area, and use that in our linear regression model. Okay? And so very often when designing a linear regression model, you may give some thought to what features you really want to construct or choose for your algorithm. Here's another closely related example of polynomial regression. And in particular, let's say you have a training set that looks like this, right? Again, this is the size, and that's the price of the house. And it looks like maybe the prices start to plateau out when they go beyond a certain size, right? And so what you may choose, so one thing you could do is fit a straight line to this data. Excuse me, that wasn't a very good straight line. But maybe what you really want to do, looking at this data, maybe what you rather do is fit a polynomial to it, or fit a quadratic function to it, so that you can capture that this curve plateaus out. So the linear model would have been h of x equals theta 0 plus theta 1x, where x is the size of the house. But maybe we instead want to fit a model equals plus theta 1x plus theta 2x squared, so that we can fit a polynomial function, right? There's like this blue curve over here. Or in fact, maybe we don't want just a second order polynomial. Maybe you think, housing prices are even more complex. Maybe you think housing prices would come up, plateau a little bit, and then pick up again. And so this red curve, maybe you can fit a third order polynomial to it. Theta 2x squared plus theta 3x cubed. I don't know. Or maybe even other models. Okay, so this would be the red curve would be a cubic function, or a third order, meaning a third order polynomial. The blue curve would be a quadratic function, and the green curve is just a linear, right? Just a linear straight line fit to the data. Sorry about the two green lines. One of them was a very badly drawn line, I guess. So let's see how we would do this, or let's see how we would maybe fit the cubic model. If we want to fit that model, we're saying that the price of a house we're going to approximate as, right? Let's see. Let me write this as right. So linear regression, right? We have that, the output is theta 0 plus theta 1x1, theta 2x2, theta 3x3. And what we would like this to be is theta 0 plus theta 1 times the size of the house plus theta 2 times the size of the house squared plus theta 3 times the size of the house cubed. So the way you can achieve this is, well, you set the first feature x1 to be equal to the size of the house in square feet. x2, you just take the size of the house in square feet and you square that. And x3, you take the size of the house in square feet and you take the cube of that. And if you create features x1, x2, x3 and plug them into linear regression as follows, just with right, so x2, if you have a house that is, say, 750 square feet, then you would set feature x2 for that house to be 750 squared, right? And then feature x3 would be 750 to the power 3. And so using these features, x1, x2, x3, if you plug it into this formula and just run, and just treat these as features as though someone else had given these features to you, and just run linear regression as usual, then you'll be fitting a cubic polynomial to the data. Just one word of caution. Suppose the size of a house ranges from 1 to 1,000 square feet, say, instead of 2,000, let me just say 1,000. Then notice that x2 will range from 1 to 1,000,000, right? That's 1,000 squared. And x3, if it's the cube, will range from 1 to, let's see, 10 to the 9. Okay? And so with this sort of polynomial regression model, your three features, x1, x2, x3, will take on very different ranges of values. And so if you have these sorts of features, you might remember to rescale the features, right, to have comparable ranges. Like we talked about in the earlier video, so that the contours of j of theta, right, don't end up these extremely elongated ellipses, which might take linear regression a long time to try to minimize. And of course, we're not just limited to polynomial regression. In fact, if let's see, if you're called, let's say we were to fit a second order polynomial, right? Say 1x plus theta 2x squared, where x is the size of the house, right? In that setting, if you had training data that looked like this, right, then it looks like maybe a polynomial function could be a reasonable fit to this data. But of course, a polynomial function, or certainly a quadratic function, eventually this will dip back down, right? That's what a quadratic function looks like. So maybe a quadratic function isn't such a good choice because quadratic function dips back down. And if you look at this data and you decide that this is better modeled with a square root function plus theta 2 square root of x, right? And so this is really theta 1 times the size of the house plus theta 2 times the square root of the house. Then again, there's nothing that stops you from choosing this type of model. And for this example, maybe this is actually a better model because if you take this model with a square root thing as a feature, then maybe you can capture something like this, that where the housing size keeps on going up, but won't ever dip back down as the size of the house increases. Okay, so you have a complete freedom to choose other features like that as inspiration may strike. To wrap up, in this video we talked about constructing features, such as constructing a feature of the lot size, or the size of the lot of land or the plot of land, such as by computing the frontage of the house times the depth of the house. So that's one way you can choose features. And we also talked about choosing features like x1 equals size, x2 equals the square of the size, x3 equals the cube of the size, and so on, as well as other features. And by choosing different choices of features, you can get linear regression to choose to fit an extremely rich class of polynomial and other models. In later videos, we'll talk about automatic ways to choose amongst these different types of features. So, for example, do you want to fit a linear function, or do you want to fit a quadratic function, or do you even want to fit a cubic function, or an even higher order polynomial? And so how do we automatically, or how do we make these choices of, say, what degree polynomial to fit to the data? In later videos, we'll talk about algorithms for making these sorts of choices automatically. But for now, just be aware that you have a choice in the features you use in linear regression. And by choosing complex features like these, you can fit very non-linear functions as well.